The universe is a beautiful enigma, but lurking within its vastness are forces so destructive, so incomprehensibly terrifying, that they defy human imagination. From rogue planets drifting through the void to cosmic cataclysms that could erase entire galaxies in an instant, these phenomena serve as chilling reminders of our fragility in the cosmic scale. As we journey through the most terrifying things in the universe, brace yourself for a reality where even the laws of physics can turn against us. Antimatter collisions, the universe's ultimate annihilator. Antimatter, the enigmatic twin of ordinary matter, represents one of the most destructive forces in the universe. When antimatter meets matter, they annihilate each other in a burst of pure energy. This process, described by Einstein's equation, reveals the sheer power locked within even the tiniest particles. In a single collision, the entire mass of the two particles is converted into energy, making antimatter interactions among the most energetic phenomena in existence. At the atomic level, antimatter consists of particles identical to ordinary matter, except they carry opposite charges. For example, an antiproton carries a negative charge, while a positron, the antimatter counterpart of an electron, carries a positive charge. When these particles collide with their matter counterparts, they release gamma rays of extraordinary intensity, creating a flash of energy that dwarfs many natural processes. Antimatter exists in trace amounts, usually produced in high-energy environments like supernovae or the accretion disks of black holes. But imagine an event on a galactic scale, a collision between a large antimatter cloud and a matter-dominated region of space. The results would be cataclysmic, releasing energy equivalent to billions of nuclear explosions in mere moments. Think about a made-up situation in which an antimatter-rich galaxy moves into a matter-dominated galaxy. Antimatter destruction would start a chain reaction as stars and cosmic matter mix. It's possible for whole solar systems to explode, sending gamma rays and other high-energy particles through space and wiping out planets and upsetting the natural balance of nearby areas. The energy released in these collisions is unparalleled. For instance, a single gram of antimatter annihilating with matter would produce as much energy as detonating 42 kilotons of TNT, comparable to the bomb dropped on Nagasaki. On a larger scale, the annihilation of planetary masses could generate energy levels surpassing those of supernovae, illuminating entire galaxies with their destructive brilliance. Some theoretical studies say that areas of antimatter could be left over from when the universe was young, and there were almost equal amounts of matter and antimatter. One of the biggest puzzles in modern physics is why the world prefers matter to antimatter. Some experts think that antimatter galaxies may still be out there, but they may be hidden in the farthest reaches of the universe. When these types of galaxies collide with matter-dominated ones, they could release an enormous amount of energy that could change the structure of the universe itself. These events pose not only a scientific puzzle, but also a potential hazard for advanced civilizations. If a planet or spacecraft were caught near an antimatter-matter collision, the resulting gamma radiation and energetic particles would annihilate everything in their path. Shielding against such forces would require technologies far beyond anything we currently possess, including advanced materials that could withstand the equivalent of standing next to a supernova. To harness the destructive potential of antimatter, some have speculated about its use as a weapon. A single kilogram of antimatter could theoretically produce the energy of 47 megatons of TNT. This makes antimatter the ultimate power source, or ultimate threat, depending on its application. But the rarity of antimatter and the immense energy required to produce and store it safely make it more of a theoretical danger than a practical one for now. Even in smaller quantities, antimatter events have cosmic consequences. When antimatter interacts with interstellar gas or dust, it creates bright, transient gamma-ray signals detectable by telescopes. These signatures offer a glimpse into high-energy processes across the universe, helping scientists understand the conditions that produce antimatter and its role in shaping the cosmos. Dark star ignitions, galactic behemoths born of darkness. Dark stars, which are hypothetically large objects made of dark matter, are some of the strangest and scariest things that astronomy has come up with. Dark stars might get their power from dark matter destruction, a process that is just as mysterious as dark matter itself. Normal stars get their power from nuclear fusion. These cosmic giants could get millions of times bigger than the Sun, making them much bigger than regular stars. Scientists believe that dark stars could have existed during the universe's earliest epochs, forming when clouds of hydrogen and helium interacted with dense pockets of dark matter. Unlike ordinary stars, dark stars would not emit light in the traditional sense, but could glow faintly due to the annihilation of dark matter particles within their cores. This annihilation releases bursts of energy that sustain the star without the need for nuclear reactions. The sheer scale of dark stars makes them unparalleled in their potential for destruction. If one were to ignite violently, perhaps due to the accumulation of ordinary matter or a collision with another massive object, the results could devastate entire galaxies. The energy released from such an event could rival the combined output of millions of supernovae, creating shockwaves that propagate across the cosmos. When a dark star starts to burn, it releases a lot of high-energy particles. These emissions could make nearby star systems less stable, which would remove the atmospheres of planets and make whole areas of space unusable. Though unlikely, the idea that dark stars could form in our time is not completely thrown out. If dark matter patches came together in areas of space with a lot of matter, they might create a new generation of dark stars. Such an event would completely change the way any nearby galaxy works, releasing forces that would make it hard for us to understand how the universe works. Even stranger, dark stars may have something to do with how black holes form. Black holes of a size and strength that have never been seen before could form as they fall apart under their own gravity. These dark star-born black holes could explain some of the giant black holes seen at the centers of galaxies. This would connect the study of dark matter with things that can be seen in space. Quasars, cosmic lighthouses of destruction. Quasars are some of the strangest and most powerful things in the universe. They give off so much energy that they can light up whole galaxies. These cosmic lanterns are powered by supermassive black holes at the centers of busy galaxies. Their beams of light can sterilize large areas of space, making them both amazing and scary. When you learn about quasars, you get a glimpse of how really violent the universe is. As much as 1 billion or more times the mass of the Sun, a giant black hole is at the center of every quasar. Accretion circles, which are huge whirling structures made of gas, dust, and other matter moving toward the event horizon, surround these black holes. Friction and gravity heat up the matter in the accretion disk, and it sends out huge amounts of energy in all forms of electromagnetic radiation, from radio waves to X-rays. This process makes the quasar into a lighthouse that can be seen from billions of light years away. Not only are quasars bright, they are unbelievably bright. It is possible for a single quasar to shine brighter than 1 trillion suns, making it visible from the farthest parts of the known universe. This brightness comes from the quick turning of matter into energy. As matter falls toward the black hole, very little of it passes the event horizon. The rest is cooked to such high temperatures that it gives off as much energy as millions of supernovae. The relativistic jets that come from quasars are one of the most interesting things about them. High-energy particles are thrown out of the poles of the supermassive black hole at speeds close to the speed of light. They go for thousands or even millions of light years and cut through the space between galaxies, causing terrible damage. Anything that gets hit by these jets is blasted with powerful radiation, which destroys atmospheres, sterilizes planets, and stops star formation in whole areas of space. The danger posed by quasars is not hypothetical. Observations have shown that quasar jets can affect galaxies millions of light years away, heating interstellar gas to such temperatures that it becomes incapable of collapsing to form new stars. This process, known as quasar feedback, can effectively shut down star formation in a galaxy, leaving it barren and lifeless. Quasars are also closely linked to galaxy collisions and mergers. When galaxies collide, the gravitational chaos often funnels large amounts of gas and dust toward their central black holes, triggering quasar activity. These events are relatively short-lived on cosmic timescales, lasting only a few million years. However, during their active phases, quasars can reshape the galaxies that host them, expelling gas and dust and altering their overall structure. In the world, quasars do more than just destroy things. They are also very important to our knowledge of how the universe evolved. Astronomers use quasars as cosmic landmarks to figure out where matter is spread out in the universe and to study the structure of the universe on a big scale. Scientists can study the very distant past with quasars' very bright light, which takes billions of years to reach Earth. Because of this, they are very useful for understanding the early universe, like how galaxies formed and how gas between galaxies behaved. Even though they are very important to science, quasars are still a secret. One thing that really stumps scientists is why some galaxies have quasars and others don't. The appearance of a quasar is thought to depend on the amount of matter that can feed the giant black hole. Quasars are more likely to be found in galaxies that have a lot of gas and dust, especially after they have merged or gone through other events that change their structure. The study of quasars has also led to groundbreaking discoveries about black holes and their environments. Observations have revealed that supermassive black holes and their host galaxies are intricately connected, with the growth of the black hole influencing the evolution of the galaxy and vice versa. This relationship is evident in the correlation between the mass of a galaxy's central black hole and the properties of its bulge, a discovery that has reshaped our understanding of galactic dynamics. While quasars are most commonly associated with the early universe, they are not entirely a relic of the past. Some quasars remain active in the present day, though they are less common due to the scarcity of readily available fuel. However, as galaxies continue to collide and merge, new quasars may emerge, reigniting the violent processes that defined the universe's infancy. Quasars also make us wonder what will happen to the Milky Way and Andromeda. When these galaxies crash into each other in about 4.5 billion years, their center black holes will probably join, which could cause quasar activity. If this happens, the quasar that follows could have huge effects on any living things that are still in the area, by releasing radiation and throwing off the delicate balance of planetary systems. Galaxy-wide electromagnetic pulse, the ultimate cosmic blackout. Think about a situation in which the heartbeat of a whole galaxy stops. A galaxy-wide electromagnetic pulse, EMP, is a possible event that could affect millions of star systems at the same time and be on a scale that is hard to imagine. EMPs are usually caused by high-altitude nuclear explosions or solar flares, but a galaxy-wide EMP would be caused by something very strange in the universe, like a giant black hole erupting with a lot of energy or two neutron stars crashing into each other. Electrical power spikes are caused by an EMP, which is a burst of electromagnetic radiation that reacts with charged particles. On a cosmic scale, this EMP's cause would probably be a disaster so terrible that scientists don't even know how to explain it. One possibility is a gamma-ray burst, GRB, that comes from a supernova or the merging of two neutron stars. Huge amounts of gamma radiation are released by these events, which could ionize large areas of interstellar space. The aftermath of a galaxy-wide EMP would be catastrophic for any advanced civilizations relying on electronic technology. Star systems within the affected region would experience widespread failures in communication, navigation, and life support systems. Satellites orbiting planets would be fried by the intense radiation, rendering interstellar communication impossible. On a more apocalyptic scale, the EMP could destabilize planetary magnetospheres, exposing worlds to deadly cosmic rays. Such an event would not only affect technology, but also disrupt the delicate balance of astrophysical phenomena. Pulsars, which serve as natural beacons for measuring galactic distances, could be drowned out by the electromagnetic chaos. Similarly, the interactions of charged particles within nebulae and stellar nurseries might be altered, slowing or even halting star formation in affected regions. A galaxy-wide EMP could have effects that last a long time after it hits. Galactic magnetic field lines could be used to spread electromagnetic disturbances over thousands of light years. Whole societies could be left in the dark, unable to rebuild without the tools that made their lives possible in the first place. One of the most disturbing things about this behavior is that it might not happen as expected. A galaxy-wide EMP is more likely to happen without notice than a local EMP, which can often be predicted by looking at how the sun is acting or how technology is changing. Advanced science tools might be able to find signs of things to come, like gravitational waves or bursts of high-energy radiation, but there wouldn't be much time to get ready. The idea of a galaxy-wide EMP is still just a guess, but it's a stark warning of how vulnerable we are in a world run by forces we can't even imagine. Even the most advanced science models can't explain how big and powerful these events are. They are pushing the limits of what we know about cosmic events. The thought of the lights of a whole galaxy going out in an instant is scary for any species that depends on technology. Rogue quasar bursts, cosmic death rays. A rogue quasar burst is not limited by the space of its mother galaxy. When its jets line up with a nearby galaxy, or even worse, an area of space where life could exist, terrible things could happen. These jets, which are mostly made up of high-energy particles and gamma rays, are strong enough to wipe out entire areas of space, killing any living things that might be in their way. The process begins with the quasar's feeding frenzy. As gas, dust, and even entire stars are consumed by the supermassive black hole, magnetic fields channel the infalling material into twin beams of energy that shoot outward at near light speed. If one of these beams happens to intersect another galaxy or planetary system, it's like focusing the universe's deadliest laser on an unsuspecting target. For planets caught in the direct path of a quasar burst, survival is impossible. The gamma rays would strip away a planet's atmosphere, leaving its surface exposed to cosmic radiation. Ozone layers would disintegrate, rendering even the most resilient forms of life vulnerable. Oceans would evaporate, and surface temperatures would soar to lethal levels. On a broader scale, a quasar burst could disrupt the chemical composition of entire star systems, halting the formation of new stars and planets. But that's not the end of the danger. Galactic ecosystems could also become unstable because of rogue quasar bursts. The strong radiation and particle flow could mess up molecular clouds, which are where stars are born, stopping new generations of stars from forming. This problem could turn a galaxy that was once full of life into a barren void over time. It's a race against time to find rogue quasar bursts. Advanced telescopes on Earth and in space are always keeping an eye on quasars and finding the ones that have jets that are actively moving. The light from a quasar burst might not reach us for millions of years, though, because of how far away it is. This means that the event might have already happened by the time we see it. The warning probably wouldn't come in time if Earth were in the path of such a burst. The size and strangeness of rogue quasars make them especially scary. Unlike supernovae, which happen in a small area of space, quasars happen on the scale of the entire galaxy, with jets that can reach hundreds of thousands of light years. Their power is so great that even places far from the straight path of a jet could be affected by its effects, such as higher amounts of cosmic radiation and problems with star formation. The Great Attractor, the cosmic mystery that pulls us all. The Great Attractor is a strange force of gravity that pulls galaxies together over hundreds of millions of light years. As it sits behind the zone of avoidance, which is covered by the thick plane of the Milky Way, it is hard to figure out what it is. It is pointing toward the Hydra Centaurus supercluster. Even though this cosmic cloud is there, you can't deny that it has an effect on our local group of galaxies, which includes the Milky Way. The existence of the Great Attractor was first inferred in the 1970s and 1980s, when astronomers noticed peculiar velocities in nearby galaxy clusters. Instead of merely expanding outward due to the universe's expansion, galaxies in the vicinity of Hydra Centaurus appeared to be deviating from their expected paths. Something massive, unimaginably massive, was pulling them inward. What makes the Great Attractor terrifying isn't just its size, but the sheer mystery surrounding its nature. Estimates suggest it could be equivalent to tens of thousands of galaxies worth of mass, yet its exact composition remains unknown. It could be a supercluster of galaxies, or an aggregation of dark matter and other exotic substances. Some theorists even propose it might be a remnant of a more ancient and violent phase in the universe's history. Not only do individual galaxies feel the pull of the Great Attractor, but whole superclusters do too. About 600 kilometers per second is the speed at which the Milky Way, the Andromeda Galaxy, and other galaxies in our local group are rushing toward it. This journey, which we can't see or feel because it happens so quickly, changes the structure of the world on a larger scale. The Great Attractor isn't the only one, though. It's part of the Laniakea supercluster, which is an even bigger structure in space. It covers more than 500 million light-years and has tens of thousands of galaxies in it. The Great Attractor is like a black hole on a cosmic scale, pulling in matter like a gravitational hub in this very large network. If humanity ever ventures far enough into intergalactic space, the influence of the Great Attractor could pose existential challenges. Navigation across such immense distances would require precise calculations to account for the gravitational distortions it causes. For spacecraft traveling at relativistic speeds, even slight deviations could lead to catastrophic outcomes. Also, the pull of the Great Attractor makes me worry about the future of the universe. The universe as a whole is growing because of dark energy, but areas dominated by gravity can stop this growth. In these places, galaxies and galaxy clusters might finally join together to form huge groups that go against the general trend of cosmic dispersion. This dance of gravity could cause chaotic crashes, the formation of very dense areas, and the destruction of smaller buildings. One of the most interesting and scary ideas is that the Great Attractor might be linked to even bigger gravity anomalies, like the Shapley supercluster that lies beyond it. All of these systems work together to make a kind of cosmic order, with bigger and bigger things controlling the gravitational field. If the Great Attractor is just a stop in a bigger flow of gravity, then we still don't fully understand how the universe is put together. Despite its overwhelming influence, the Great Attractor remains a scientific enigma. Its position in the zone of avoidance makes direct observation challenging, as dust and gas in the Milky Way obscure the view. However, advances in infrared and X-ray astronomy have provided glimpses into its hidden depths. These observations have revealed clusters of galaxies and evidence of massive structures, but much remains speculative. From a philosophical point of view, the Great Attractor represents how the world doesn't care about human lives. It works on such huge scales, and with such huge forces that human worries are small in comparison. But it also makes us feel awe because it reminds us of how many complex and linked forces form the universe. Colliding galaxies, the cosmic smash that shapes the universe. When galaxies crash into each other, it's not just a light brush or a slow joining. It's a huge, violent event that changes the very structure of the universe. Even though stars in galaxies are very far apart and don't usually crash into each other directly, the gravitational pull of these huge systems of stars, gas, and dark matter can send shockwaves millions of light years away. A crash like this is bound to happen in the Milky Way, and it is both a beautiful and scary reminder of how chaotic the universe is. The Milky Way and its neighbor, the Andromeda Galaxy, are on a collision course set to unfold approximately 4.5 billion years from now. Though the timescale may seem incomprehensible, the consequences of this galactic encounter are already being studied in great detail. Andromeda, slightly larger and more massive than the Milky Way, will approach at a relative speed of 400,000 kilometers per hour. Over the course of billions of years, their mutual gravitational pull will draw them together, sparking a series of dramatic changes. At first, the two galaxies will pass close enough for their gravitational forces to begin distorting each other. This tidal interaction will stretch and warp their structures, creating massive tidal tails, long streams of stars and gas pulled away from their original positions. These interactions will also trigger intense bursts of star formation, as clouds of gas and dust are compressed by the gravitational chaos. These new stars will burn brightly for millions of years, lighting up the night sky in a way that has never been seen before. But this cosmic event has the power to be both beautiful and deadly. As the galaxies get closer together, the center black holes, which are each millions of times the mass of the Sun, will start to affect each other. It's possible that these very large black holes will finally join together, releasing huge amounts of energy in the form of gravitational waves. The uniform black hole that forms could be at the center of the new galaxy and eat anything that gets too close. For any life forms that might exist on planets within these galaxies, the collision could be apocalyptic. The gravitational upheaval could eject stars from their orbits, hurling them into intergalactic space. Entire solar systems could be destabilized, with planets cast adrift into the cold void. Even if a planet like Earth were to remain in a stable orbit, the increased radiation from newly formed stars and energetic black hole activity could make survival impossible. Beyond the Milky Way-Andromeda collision, galaxy mergers are common across the universe. Observations of other galactic encounters provide a glimpse of our own future. The antennae galaxies, for example, are in the midst of a collision that has produced spectacular starburst regions and tidal tails. Similarly, the Cartwheel Galaxy owes its unique ring-like structure to a violent collision with a smaller galaxy. While galactic collisions are often depicted as violent and destructive, they also play a critical role in the evolution of the universe. These interactions help galaxies grow, mixing their contents and redistributing material in ways that drive the formation of new stars, planets, and other cosmic structures. Over time, the chaotic energy of a collision gives way to a new equilibrium as the galaxies merge into a single, larger entity. It is likely that the Milky Way and Andromeda will merge into a huge circular galaxy, which is sometimes called Milkomeda. The shape of this galaxy will be smoother and more even than the spiral shapes of the ones that came before it. It will take billions of years for the two to merge, but the end result will show how powerful gravity forces are in changing the shape of the world. There is, however, a bigger, scarier story behind these accidents. As the universe grows, galaxies that are pulled together by gravity, like those in the local group, will finally join together to form bigger structures. While this is going on, galaxies that are not gravitationally linked will move farther apart as the universe expands faster. Because of this dual dynamic, galaxies will continue to crash into each other in the near future, but the structure of the universe as a whole will become more and more separated. One of the most interesting things about galaxy encounters is how they feed supermassive black holes. When these things happen, gas and dust are pushed toward the centers of galaxies, feeding their central black holes and starting the formation of quasars, which are very bright objects driven by matter accretion. These quasars can shine brighter than whole galaxies and send out huge amounts of energy into space. The impact between the Milky Way and Andromeda will be a big deal in our cosmic neighborhood. But it's only one part of the story of how galaxies have changed over time. During the past of the universe, many galaxies have crashed into each other, joined together, and then split apart again, making the complex web of structures we see today. The fact that these things are happening is a reminder of how changing the world is. Even the biggest buildings are always moving because of gravity. Vacuum collapse, the universe's silent assassin. The idea of a vacuum collapse is one of the scariest things that theoretical physics has ever come up with. It says that the world is in a false vacuum state, which is a brief and unstable arrangement of energy. If this fake vacuum suddenly turned into a more stable true vacuum, It would set off a terrible chain reaction that would change the very fabric of reality at the speed of light. There is no way to escape or stay alive after this event that ends the world. Quantum field theory, which says that empty space isn't really empty, is where the vacuum collapse theory gets its ideas from. Instead, space is made up of quantum fields, and each one stands for a different amount of potential energy. The universe is like a marble sitting dangerously on the side of a hill in the false vacuum situation. It is solid, but it is not the lowest energy state possible. A quick change, like a quantum push, could make the rock roll down into the real vacuum, setting off a chain of changes that would affect everything in the universe. The sneakiness of vacuum failure is what makes it so scary. Unlike observable cosmic threats such as black holes or gamma-ray bursts, a vacuum collapse would offer no warning. The event would spread at the speed of light, and since nothing moves faster than light, it would arrive instantly everywhere it went. It would be too late to understand or do anything about it by the time it started to happen in our part of space. The changes brought about by a vacuum collapse would be all-encompassing. Physical constants such as the speed of light, gravitational forces, and the strength of fundamental interactions could all shift dramatically. Matter as we know it might cease to exist, replaced by entirely alien forms governed by the new laws of physics. Stars, planets, and even the particles that make up atoms would be obliterated in the wake of the transition, leaving behind a universe utterly unrecognizable. Though the idea of vacuum collapse is theoretical, some scientists argue it's not entirely outside the realm of possibility. The discovery of the Higgs boson in 2012 provided a critical piece of evidence for the standard model of particle physics. However, subsequent calculations based on the properties of the Higgs boson have raised unsettling questions about the stability of our universe. These calculations suggest the energy state of the Higgs field might place our universe precariously close to the boundary between stability and instability, increasing the plausibility of a vacuum collapse scenario. Cosmic inflation, a time when the universe grew very quickly in its early stages, is also related to the vacuum collapse topic. Some ideas say that inflation might leave behind fake vacuums all over the universe. These could be leftovers from the high energy state that caused the universe to grow so quickly. Even though these areas are rare and far away, they could be the start of future vacuum decay events that could destroy whole parts of the universe. While vacuum collapse is purely theoretical, its implications extend far beyond existential dread. The study of false vacuums and related phenomena has driven significant advancements in quantum field theory, cosmology, and high-energy physics. Scientists have used the concept as a thought experiment to explore the boundaries of what we know about the universe and the forces that govern it. It has also influenced our understanding of black holes, particle accelerators, and the behavior of quantum fields in extreme environments. Particle accelerators like the Large Hadron Collider, LHC, often come up in discussions about vacuum collapse. Some have speculated that high-energy experiments conducted in these facilities could inadvertently trigger a vacuum decay event. However, physicists widely agree that such fears are unfounded. The energy levels achieved in particle accelerators are minuscule compared to those naturally occurring in cosmic events like supernova or gamma-ray bursts, which haven't caused vacuum collapse despite billions of years of opportunities. The prospect of vacuum collapse has also inspired philosophical debates about the nature of existence and the limits of human knowledge. If our universe is indeed in a false vacuum state, it raises profound questions about why it exists in this configuration and what, if anything, lies beyond the true vacuum. Such discussions often blur the lines between science and metaphysics, delving into realms that are as speculative as they are unsettling. Since there isn't strong proof for or against vacuum collapse, scientists keep looking into similar phenomena to try to understand them better. Observations of cosmic inflation, the study of quantum fields, and high-energy physics tests all add to what is known about the void, and may one day help us understand what it is really like. For now, the idea of vacuum collapse is just a warning of how unpredictable the world is and how fragile life is. Strange matter, the universe's ultimate domino effect. Strange matter is one of the scariest ideas in physics. It is a made-up state of matter that might appear in very rare situations. It is thought to form when quarks, which are the building blocks of protons and neutrons, are adjusted so that they are in a more stable arrangement that includes strange quarks. There is a chance that this strange matter is very dangerous, especially if it combines with regular matter. The idea of strange matter emerges from the study of neutron stars, where matter is compressed to densities unimaginable on Earth. Within the core of these stars, it's theorized that neutrons could break down into their constituent quarks, creating a dense soup of up, down, and strange quarks. This strange quark matter, if it exists, could be the most stable form of matter in the universe, making it capable of catalyzing a terrifying chain reaction. If strange matter comes into contact with regular matter, it might convert that matter into more strange matter, releasing energy in the process. This runaway conversion could theoretically consume entire objects from planets to stars, leaving behind only a strange matter core. This process, known as strangification, represents a scenario where even a microscopic piece of strange matter could trigger cataclysmic destruction. The potential sources of strange matter are vast, with neutron stars being the most likely candidates. Collisions between neutron stars or their interaction with other cosmic bodies could eject strange matter into space. These particles, sometimes referred to as strangelets, could travel vast distances, posing a potential threat to anything they encounter. The idea that a single rogue strangelet could wander into our solar system and initiate stringification is the stuff of cosmic nightmares. One frightening and unique thing about strange matter is that it might be able to bounce back. Strange matter is thought to be very steady under a lot of different situations, while normal matter can break down and become unstable. Because they are so stable, strangelets could live in the hard conditions of space and stay whole for billions of years as they travel through the universe. While strange matter remains theoretical, scientists are actively studying its potential properties through astrophysical observations and high-energy experiments. Observations of neutron star collisions, detected through gravitational wave astronomy, may provide indirect evidence of strange matter. Similarly, experiments at particle accelerators like the Large Hadron Collider, LHC, explore conditions that might create strange quarks, shedding light on the feasibility of strange matter formation. Despite its speculative nature, the concept of strange matter raises profound questions about the universe's underlying stability. If strange matter is indeed more stable than regular matter, it challenges the assumption that our universe's current configuration is the most energetically favorable. This idea aligns with broader concerns about metastability in physics, echoing fears of vacuum collapse and other fundamental cosmic threats. Strange matter could have effects that go beyond instant destruction. Strange matter could completely change the structure and motion of the world if it were to replace regular matter on a big scale. Strange matter stars and galaxies would give off different kinds of radiation, which would have an impact on everything from the growth of the universe to the habitability of worlds. These changes would have an effect on the whole universe and make a whole new order in the universe. Some scientists speculate that strange matter could explain certain astrophysical anomalies. For example, unusually dense objects observed in distant galaxies might be remnants of stars transformed into strange matter. Similarly, unexplained bursts of radiation or gravitational waves could hint at interactions involving strangelets or other manifestations of this exotic material. It's also possible that strange matter will affect how we explore the universe. If strangelets exist, they might be dangerous for spaceships and humans going beyond the magnetic field that protects Earth. As people go deeper into space, making devices that can find and reduce the risks of strange matter may become more important. Strange matter also makes it possible to think about advanced societies, which is interesting. It is thought that strange matter could be used as a source of energy, or to build advanced tools if it is as stable and powerful as thought. However, using such a flammable material would require a level of accuracy and knowledge that is far beyond what we have now. Any society that could use strange matter safely would probably be a lot further along than humans. Primordial black holes. Ancient threats from the birth of time. Primordial black holes, PBHs, are thought to be some of the most mysterious and old things in the universe. PBHs are thought to have formed very soon after the Big Bang, when the universe was a hot, dense soup of energy and particles. Stellar black holes, on the other hand, are made when very big stars fall apart. If these strange items exist, they might be remnants of the very fabric of space-time, showing how chaotic things were when the universe was young. The creation of primordial black holes is linked to quantum fluctuations in the early universe. These fluctuations cause some regions of space to become denser than others, and under the extreme pressures of the Big Bang, these dense regions could have collapsed into black holes. The mass of a primordial black hole would depend on the size of the fluctuation that created it, meaning they could range from microscopic to thousands of times the mass of the Sun. One of the most frightening things about primitive black holes is that they could be many different sizes. PBHs are not like stars, which are mostly the same size. They can be as small as a proton or as big as a galaxy. Small PBHs, which are sometimes called micro-black holes, would give off energy through Hawking radiation and slowly disappear over time. However, bigger PBHs might be able to stay in the background forever, hidden in the vastness of space. Plus, the idea that PBHs are invisible predators makes them even more mysterious. Even if they don't give off visible light, their gravity could change the way close stars, planets, and even galaxies move. If a primordial black hole went through a solar system, it might mess up the paths of the planets, throwing them into interstellar space or causing terrible crashes. Primordial black holes have also been proposed as a candidate for dark matter, the enigmatic substance that makes up approximately 27% of the universe. If PBHs are numerous and massive enough, they could account for a significant portion of dark matter's gravitational effects. Detecting them would not only confirm their existence, but also provide critical insights into one of the universe's greatest mysteries. The search for PBHs is a frontier of astrophysical research. Scientists use a combination of observational techniques and theoretical models to hunt for these elusive objects. Gravitational lensing, where the gravity of a black hole bends the light of background stars, is one method used to detect PBHs. Similarly, gravitational wave detectors like LIGO and Virgo may capture signals from PBH mergers, offering another way to identify them. Even though they have been around for a very long time, primordial black holes are still important to current cosmic events. Some experts think that they might be the building blocks for the giant black holes that are found at the centers of galaxies. According to this idea, PBHs were spread out in the early universe and slowly gathered matter over billions of years, turning into the huge black holes we see today. The idea that there are small PBHs in our solar system is another scary thought. It's possible that these weak things could be a danger that you can't see. Even though it is very small, a micro black hole's strong gravity pull could destroy a small area if it hit Earth. Even though this is a very unlikely situation, it shows how dangerous PBHs could be. PBHs are also a unique place to test ideas about quantum physics and gravity. Stephen Hawking, a theoretical scientist, said that black holes might give off Hawking radiation. Studying this effect could give us new information about black holes and how quantum mechanics and general relativity work together. According to this, PBHs are both a possible threat and a useful way to learn more about the world. Some theorists have even speculated that PBHs could be harnessed for advanced energy production. By capturing the energy released through Hawking radiation, a sufficiently advanced civilization might use PBHs as a nearly limitless power source. However, the technical challenges and risks associated with manipulating black holes make this idea far from practical for humanity at present. One question that people still have about PBHs is why they haven't been found yet, if they exist. Their hard-to-find nature could be because they are small, spread out, or able to mimic the effects of other astronomical events. Another possibility is that PBHs never formed in the first place. If this is the case, their theory may need to be changed based on new information. The event horizon, a point of no return. Undoubtedly, one of the oddest and darkest things in the universe is the event horizon of a black hole. It stands for the line past which nothing, not even light, can get away. Even though black holes can't be seen, the event horizon is where they become clearly visible. This is where the gravity pull is so strong that it is physically impossible to escape. This border isn't just an interesting science question, it's a huge problem for how we think about physics. The event horizon forms as a result of the immense gravitational collapse of a massive object. When a star exhausts its nuclear fuel and collapses under its own gravity, the core can become so dense that it warps space-time to an extreme degree. At this critical boundary, the escape velocity exceeds the speed of light. Once something crosses this threshold, it is irrevocably drawn into the black hole's singularity, a point of infinite density. What makes the event horizon particularly unsettling is its paradoxical nature. From an outside observer's perspective, anything falling toward the event horizon appears to slow down and fade, never quite crossing it due to the extreme warping of time. However, for the object falling in, the event horizon is crossed in finite time, and it is pulled inexorably toward the singularity. This dual perspective highlights the strange interplay between relativity and gravity in the realm of black holes. As a one-way barrier, the event boundary is one of the most interesting things about it. Atoms and mass can pass through the black hole, but nothing can get out. The conservation of information is one of the most important ideas in physics, and this trait has huge effects on it. Stephen Hawking said that black holes give off radiation, which is now called Hawking radiation. This means that black holes may slowly disappear over time. The information paradox comes up, though. What happens to the information that is carried by matter and energy when they fall into a black hole? The study of event horizons has led to groundbreaking theoretical work, particularly in the quest to reconcile quantum mechanics with general relativity. The holographic principle, for instance, suggests that all the information contained within a black hole might be encoded on its surface area, the event horizon. This concept has inspired new approaches to understanding the fabric of the universe itself. There are also a lot of high-energy events happening near the event horizon. As things move in a path toward a black hole, they build up an accretion disk, which is a ring of gas and dust that is very hot and spins. X-rays and gamma rays are very bright because of the friction inside the disk. Black holes are some of the brightest things in the universe. This discharge happens outside the event horizon, but it is caused by the black hole's very strong gravity. It is possible for someone just outside the event horizon to experience a very large amount of time dilation. For someone far from the black hole, seconds could be the same as thousands of years. Einstein's theory of relativity predicted this effect, which has been made more dramatic in science fiction. However, it is still a real effect that can be tested. The normal rules of physics are pushed to their limits close to the event horizon. This gives us a look at how the world works when things are very bad. Event horizons are not uniform across all black holes. Their size depends on the mass of the black hole. For stellar black holes, the event horizon might span only a few kilometers, while for supermassive black holes, like the one at the center of the Milky Way, it can stretch across millions of kilometers. This vast range in scale underscores the diversity of black holes in the universe. We can now directly see the shade of a black hole's event horizon thanks to recent progress in observational astronomy. The Event Horizon Telescope, EHT, took the first picture of the galaxy M87's supermassive black hole. It showed a dark core surrounded by a bright ring of light. This important discovery has made it possible to study black holes and how matter and energy behave near their event horizons in new ways. The event horizon also raises profound questions about the nature of space-time. If black holes are portals to other regions of the universe, as some theories suggest, the event horizon might mark the entryway to a wormhole or another dimension. These ideas remain speculative, but capture the imagination of physicists and the public alike. Arguably, they have a scary image. Event boundaries may also be useful in the universe. Some scientists think that black holes play a role in the formation of galaxies and the spread of matter in the universe through their strong gravitational pull. With their huge event horizons, supermassive black holes help keep the structure of the universe in place by holding galaxy cores in place. What about the idea of a rogue event horizon? It makes the conversation even scarier. A rogue black hole with a very large event horizon could move through the galaxy and eat matter without caring about what it is. These wandering giants are a scary warning of how dangerous the world really is. Cosmic voids, the empty giants of the universe. Cosmic voids are some of the most perplexing and eerie phenomena in the universe. These vast, dark regions of space span hundreds of millions of light-years and are virtually devoid of galaxies, stars, or matter. While the universe is a web of filaments filled with galaxies and clusters, cosmic voids represent the haunting gaps in this intricate structure. Unlike a barren desert, cosmic voids aren't completely empty. They contain a sparse smattering of gas, dark matter, and perhaps a few rogue stars or galaxies. However, the density of these regions is so low that they appear as near vacuums compared to the densely packed clusters around them. The Bootes void, one of the largest known, spans about 330 million light-years and contains only a few dozen galaxies, whereas a region of similar size in a denser area of the universe might hold thousands. The formation of cosmic voids is closely tied to the early stages of the universe. As matter began to clump together due to gravitational forces after the Big Bang, regions with slightly lower densities were left behind. Over billions of years, these underdense regions expanded as the denser areas became more gravitationally bound, forming galaxies, clusters, and the cosmic web. Voids, therefore, are remnants of a process that shaped the large-scale structure of the universe. Cosmic voids may sound peaceful because they are empty, but they make it hard to understand how the universe works. Because there is almost no matter in these areas, they are perfect places to study dark energy, the unknown force that is speeding up the growth of the universe. Regular matter doesn't have as much of an effect on gaps' growth rates, which may help us understand how dark energy works on a cosmic scale. Interestingly, voids are not uniformly dark. The residual matter within them can occasionally form stars, galaxies, or even faint galaxy clusters. These void galaxies are often isolated and exhibit unique characteristics compared to their counterparts in denser regions. They are typically smaller, have low metallicity, and experience slower rates of star formation. Observing these galaxies provides valuable data on how environments influence galactic evolution. The way they affect light is one of the most interesting things about cosmic gaps. Gravitational lensing happens to light from faraway galaxies as it travels through a void, but in a strange way. In contrast to dense groups, which bend and increase light, gaps have a slight effect of stretching and dimming light that is called cosmic magnification. Astronomers can use this effect to indirectly map gaps by looking at the light from galaxies behind them. The unsettling emptiness of cosmic voids also makes us think about our own lives and our purpose in this world. If there were advanced societies in these areas, they would be very far away from everything else. The uneven spread of stars and galaxies would make it harder to communicate or explore between stars. If these civilizations could survive and grow, they might come up with very different ways of understanding the universe than those that live in denser areas. cosmic voids are not static, they evolve over time. As the universe continues to expand, these voids grow larger, pushing galaxies and matter further toward the surrounding filaments. In the far future, as the universe trends toward its heat death, voids may dominate the cosmic landscape, leaving an increasingly fragmented and desolate universe. The study of cosmic voids is a fairly new area of astronomy, but it is making great progress very quickly. Recent studies like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have drawn out thousands of voids, showing where they are and what they're made of. These studies have helped improve cosmic models and given us a better idea of how the world is put together on a large scale. Void simulations also play a crucial role in this research. By recreating voids in computational models, scientists can explore their formation and evolution under different cosmological scenarios. These simulations test theories about dark energy, dark matter, and the initial conditions of the universe. Despite their emptiness, cosmic voids are far from irrelevant. They are an integral part of the cosmic tapestry, influencing the behavior of galaxies, light, and even fundamental forces. False vacuum decay, the universe's ultimate reset button. It's both worrisome and interesting to think about the idea of false vacuum decay, a made-up event that could end the universe without warning and wipe out everything we know in an instant. This end-of-the-world event comes from quantum field theory, which says that the universe may not be as stable as we think. Being at the center of the world is the Higgs field, a quantum field that gives electrons their mass. At the moment, this field is in what we call a stable energy state, but the false vacuum theory says that this steadiness might only be a trick. It's possible for our world to change from a false vacuum, which is an energy state that seems steady but isn't, to a true vacuum, which is a more stable energy state. This change would be terrible and would change the basic rules of physics. The decay of a false vacuum would begin at a single point in space, triggered by quantum fluctuations or an extremely high energy event, such as a collision with a black hole or interaction with exotic particles. From this point, a bubble of true vacuum would expand outward at nearly the speed of light, annihilating everything in its path. The boundary of this bubble would contain immense energy, rewriting the quantum fields and physical constants that define our reality. What makes false vacuum decay particularly unsettling is its unpredictability. Unlike a supernova or black hole, which are governed by observable astrophysical processes, the transition from a false vacuum to a true vacuum could happen anywhere, at any time, without warning. There would be no forewarning or time to prepare. One moment, the universe as we know it would exist, and the next, it would be fundamentally different, or gone entirely. While this concept may sound purely theoretical, it is grounded in serious science. The discovery of the Higgs boson at the Large Hadron Collider in 2012 provided critical insights into the Higgs field and its properties. Early calculations suggested that the mass of the Higgs boson and the top quark imply that the universe is metastable. That is, it resides in a false vacuum that could decay in the distant future. However, these calculations are subject to refinement as we gain a better understanding of particle physics. If a false vacuum decay event were to occur, the consequences would be incomprehensible. The expansion of the true vacuum bubble would destroy all matter, energy, and structures it encounters, from galaxies to atoms. Even the basic forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, could be altered or cease to exist entirely. The new universe inside the bubble might have different physical laws, making it uninhabitable for any form of life as we understand it. Even though it would be very scary, the period for fake vacuum decay is thought to be very long, much longer than the age of the universe right now. Some estimates say that something like that might not happen for trillions of years, if it ever does. This long timeline gives us some peace of mind, but it doesn't completely rule out the chance. Scientists are also exploring scenarios that could accelerate false vacuum decay. High-energy cosmic events, such as the collision of black holes or the interaction of particles at energy levels far beyond our current technology, might create conditions conducive to triggering a decay. Some theorists have even speculated about the role of advanced civilizations, if they exist, in potentially accelerating or preventing such a catastrophe through their technological endeavors. The idea of false vacuum decay also makes you think deeply about what reality is and what part humans play in observing the world. As we learn more and develop new technologies, we may one day be able to control these grave risks. Are we just passengers in a universe ruled by strict quantum rules? False vacuum decay is still being studied in both astronomy and particle physics for the time being, as a way to find out if the universe is truly metastable, or if there are other unknown factors that make it more stable. Theoretical scientists keep improving models of the Higgs field and quantum vacuum states. Experiments at particle accelerators like the Large Hadron Collider and new ones will be very important in solving this cosmic puzzle. Blazars, cosmic death beams. The universe's most powerful and violent events, called Blazars, are driven by active galactic nuclei, AGN, that are giant black holes. The main thing that makes them different from other AGN is that one of their relativistic jets is pointed straight at Earth. Blazars are one of the scariest things that can happen in the sky, because these jets are moving so fast that they send out powerful radiation and particles that could destroy anything in their path. Blazars form when matter accretes onto a supermassive black hole at the center of a galaxy. This infalling material forms an accretion disk, which is heated to extraordinary temperatures, emitting vast amounts of energy. Magnetic fields surrounding the black hole twist and focus some of this energy into jets that shoot out from the poles of the accretion disk. The orientation of these jets determines the blazar's destructive potential. When one points toward Earth, the consequences can be catastrophic. The radiation emitted by a blazar jet spans the electromagnetic spectrum, from radio waves to gamma rays. Gamma rays are particularly dangerous, carrying enough energy to disrupt molecular bonds, ionize atoms, and sterilize entire regions of space. A direct hit from a nearby blazar jet could obliterate planetary atmospheres, rendering them uninhabitable. Even at great distances, the energetic particles and radiation from blazars can have profound effects on surrounding star systems and interstellar environments. One amazing thing about blazars is how different they are. In contrast to other steady celestial events, blazars can have quick and dramatic changes in how bright they are. These changes happen because of turbulence and magnetic instability in the jets, which lead to energy bursts. Astronomers who study blazars have seen their light rise by hundreds or even thousands of times in just a few hours. People call these rapid explosions blazar flares. They tell us that these cosmic death beams are very unstable and can change at any time. The nearest blazars are millions of light years away, but the amount of energy they put out is still amazing. Some blazars give off more energy in a second than the Milky Way does in a year. A blazar's deadly power comes from both its huge amount of energy and the way its jets are directed. Blazar jets focus their energy into narrow lines, making their effects stronger than from other sources of radiation that spread out in all directions. Blazars are also of great scientific interest because they offer a unique window into the behavior of supermassive black holes and the extreme conditions near event horizons. The particles within the jets are accelerated to relativistic speeds, close to the speed of light, through processes that are not yet fully understood. Studying blazars allows astronomers to probe the limits of physics, testing theories of magnetohydrodynamics, particle acceleration, and the interactions between matter and extreme gravitational forces. Blazars do more than just destroy things, they also shape the world. Their jets can interact with the medium between galaxies, moving matter and energy around over very long distances. These interactions can change how galaxies form and how structures are spread out in the universe. This shows that blazars are both killers and builders of the universe. Blazars can be dangerous in more places than just their local area. Cosmic rays, which are high-energy particles that come from Blazar blasts, can cross outer space and reach Earth. The Earth's atmosphere protects us from most cosmic rays, but the most powerful ones can get through. They can damage gadgets, make pilots more exposed to radiation, and even change the climate on Earth. Finding blazars and keeping an eye on them are very important for learning about how they might affect our galaxy and others. Astronomers study blazars with ground-based cameras and space observatories, like the Fermi Gamma Ray Space Telescope. They plan out where the blazars are and keep an eye on what they're doing. Blazars are a stark reminder of how powerful and unpredictable the universe is in a world full of both amazing and scary things. Rogue planets, the wanderers of destruction. Rogue planets are among the most unknown and terrifying threats to the galaxy. Expelled from their native star systems, these planetary masses will continue to float aimlessly in intergalactic space. A rogue planet is a frigid, dark world that isn't illuminated by its parent star and can go undetected until it gets dangerously near. They are a major threat to any solar systems they may pass through on their quiet galactic trek, including our own. Unlike planets bound to a star, rogue planets are free agents, propelled by gravitational interactions, stellar explosions, or the chaotic early formation stages of planetary systems. When massive gas giants or dense terrestrial planets are caught in these gravitational conflicts, they can be hurled out of their systems at astonishing speeds. This chaotic origin story means that rogue planets are more common than we might assume, and their presence can disrupt the delicate harmony of star systems they approach. The size and composition of rogue planets vary widely, ranging from rocky terrestrial worlds to icy giants and even failed stars known as brown dwarfs. Their diversity adds to the difficulty of detecting them, as smaller rogue planets are virtually invisible against the blackness of space. Even larger rogue planets, which might emit faint heat signatures, are often shrouded in the cold, lightless void, evading conventional detection methods. These stealthy travelers could potentially lurk undetected on collision courses with unsuspecting planetary systems. If a rogue planet were to pass through a solar system, its gravitational influence could wreak havoc. A close encounter might disrupt planetary orbits, potentially ejecting planets from their stable paths or sending them careening into one another. Even a near miss could destabilize the orbits of asteroids and comets, creating a cascade of impacts on planets, including Earth. The gravitational perturbations caused by a rogue planet could transform a serene system into a chaotic battlefield of celestial collisions. A dangerous planet entering the inner parts of a solar system, where livable worlds like Earth live, is one of the scariest possibilities. A rogue planet could cause terrible things to happen, depending on its size, speed, and path. The most dramatic and destructive result is a direct impact which could destroy any worlds in its path. Gravitational interactions could remove planets' atmospheres, change their temperatures, and kill off life on worlds that were once livable, even if they didn't make direct contact. Rogue planets are not only a threat to planetary systems, they also offer a glimpse into the extremes of survival in the universe. Despite their inhospitable nature, some rogue planets may harbor life, albeit in forms vastly different from what we know. Subsurface oceans, heated by radioactive decay or tidal forces, could provide niches for microbial life, even in the absence of sunlight. These dark, wandering worlds challenge our understanding of habitability and the resilience of life in the cosmos. Finding rogue planets is very hard, but scientists have come up with new ways to find these hard-to-find things. Gravitational microlensing, a way to find out when a planet is in front of a star, and bending the light from those stars, has worked especially well. More rogue planets should be found by space telescopes like Kepler, and new projects like the Nancy Grace Roman Space Telescope. This will help scientists learn more about how common they are and how they behave. The study of rogue planets has huge implications for our knowledge of how planetary systems work and the random processes that shape them. These wanderers show how wild and unstable the universe is, where things don't stay the same for long, and change is always going to happen. Planets that go off course show us that the universe is not a steady, ordered place, but one that is always changing and is often dangerous. Dark matter clumps, the hidden disruptors. Dark matter clumps, though invisible and undetectable by conventional means, their immense gravitational influence shapes galaxies, clusters, and even the universe's large-scale structure. While their role in holding the cosmos together is well established, the potential hazards posed by concentrated regions of dark matter, or clumps, remain a subject of both scientific intrigue and existential dread. Even though dark matter makes up about 85% of the universe's mass, no one knows what it is. Dark matter is different from normal matter because it doesn't deal with electromagnetic energy. This means that it doesn't give off, absorb, or reflect light. Because dark matter groups are invisible, they are very hard to find, even though they leave huge gravity trails. Scientists figure out if they are there by looking at the gravitational effects they have on things that can be seen, like how gravitational lensing bends light from stars. What makes dark matter clumps particularly unnerving is their potential to disrupt the delicate balance of celestial systems. These dense, compact regions of dark matter could drift silently through space, largely undetected, until they encounter a star system. When this happens, their gravitational pull could destabilize orbits, scatter asteroids, and send planets careening into new and dangerous trajectories. The exact composition of dark matter clumps is unknown, but theoretical models suggest they could range from diffuse clouds to highly dense regions. If a dense clump were to pass through a solar system, the effects could be catastrophic. The gravitational forces exerted by such a clump might pull planets out of their stable orbits, disrupting climates and ecosystems. It could also displace smaller celestial bodies, sending comets and asteroids into the inner solar system, creating a heightened risk of impacts. The Milky Way itself is believed to contain numerous dark matter clumps, with some possibly located relatively close to our solar system. While their average distribution appears to be diffuse, certain regions may harbor concentrated pockets. The prospect of a dense clump passing near or through our solar system is remote but not impossible, and its consequences would be devastating on both astronomical and geological timescales. The idea that dark matter groups might interact with black holes is one of the most confusing things about them. If a group of dark matter particles collided with a black hole, it might send out high-energy particles or waves, giving scientists a rare look into what dark matter is made of. Gravitational waves could be sent out into the universe by this collision, showing that both of the things involved are there. Dark matter clumps also pose a unique challenge to future space exploration and colonization. As humanity extends its reach into the galaxy, understanding and navigating these invisible hazards will be critical. A spacecraft unknowingly venturing through a dense dark matter clump could experience gravitational anomalies, complicating navigation and jeopardizing the mission. Regardless of the risks, dark matter clumps provide an unprecedented potential for scientific discovery. Scientists want to find out more about dark matter, which is one of the biggest questions in the universe, by looking into its structure, effects, and where it is found. More accurate maps of dark matter clumps are being made using new ways to find them, like gravitational lensing scans and cosmic microwave background studies. Future projects, such as space-based telescopes, should give us a better idea of how they behave and what they are made of. White dwarfs going. Nova. A star's fiery rebirth. White dwarfs are the remnants of stars like our Sun, left behind after they exhaust their nuclear fuel and shed their outer layers. These dense, Earth-sized stellar cores are typically stable, slowly cooling over billions of years. However, under specific conditions, white dwarfs can undergo a dramatic transformation, reigniting in a cataclysmic event known as a nova, or even a supernova. When a white dwarf is in a binary system with another star, a nova happens. The white dwarf's strong gravity pulls matter, mostly hydrogen, from its partner, creating a dense accretion ring around the dwarf. Over time, the white dwarf's surface builds up enough hydrogen for nuclear fusion to start up again, which causes an explosive explosion that happens all at once. The explosion doesn't kill the white dwarf, but it does release a huge amount of energy that quickly makes the whole system brighter than a galaxy. The most extreme case arises when the white dwarf accumulates so much material that it approaches the Chandrasekhar limit, a mass of approximately 1.4 times that of the Sun. Crossing this threshold destabilizes the star, leading to a Type Ia supernova. Unlike a nova, a supernova obliterates the white dwarf entirely, leaving behind no trace of the original star. These explosions are so luminous they can be seen across billions of light years and serve as cosmic mileposts for measuring the expansion of the universe. The energy released during these events is beyond comprehension. In a Type Ia supernova, the explosion can outshine the combined light of billions of stars in its host galaxy for weeks. The shock waves from the blast expand outward, sweeping up interstellar material and creating stunning nebulae. However, the beauty of these remnants belies their destructive power. If a white dwarf goes nova or supernova near a populated system, the consequences would be catastrophic. The radiation emitted could strip away the atmospheres of nearby planets, rendering them uninhabitable. High-energy particles from the explosion could interfere with electronics, satellites, and spacecraft over vast distances, jeopardizing advanced civilizations. Fortunately, the likelihood of such an event occurring close to Earth is extremely low, as no white dwarfs near us are currently in binary systems, conducive to these phenomena. A very important part of the universe's environment is also played by white dwarfs that go nova or supernova. Heavy elements like iron, nickel, and silicon are needed to make worlds and support life. These blasts create and spread these elements. In this way, they are both destroyers and producers, putting the building blocks of life into the world. Astronomers actively study these events to better understand stellar evolution and cosmic phenomena. Observatories like the Hubble Space Telescope and upcoming missions like the Vera Rubin Observatory are equipped to monitor novae and supernovae, capturing the early light curves of these explosions. These observations provide critical data on the mechanisms driving these events and their impact on their surroundings. Based on theoretical models, white stars in binary systems may have other, less common results. Some scientists think that when white dwarfs merge with neutron stars or black holes, they might create completely new kinds of blasts in space. Even though these events haven't been seen yet, they might have as much energy as supernovae and give us new information about how stars die and come back to life. Collapsing neutron stars, the universe's ultimate powerhouses. Neutron stars, the dense remnants of massive stars that have undergone supernova explosions, are among the most extreme objects in the universe. These stars, with masses greater than the Sun, compressed into a sphere only a few miles across, defy our understanding of matter and physics. However, when neutron stars collapse under their own gravity, the results are cataclysmic, producing some of the most powerful phenomena in existence. A collapsing neutron star often occurs in one of two scenarios: when it merges with another neutron star, or when it exceeds a critical mass by accumulating additional matter. In either case, the star can no longer support itself against gravity, leading to an implosion. The aftermath of such a collapse is typically a black hole, an object so dense that not even light can escape its grasp. A gamma-ray burst, GRB, is one of the most amazing things that can happen when a neutron star falls. These bursts are the most powerful events in the world. They give off as much energy in a few seconds as the Sun does in its whole life. It is thought that GRBs happen when two neutron stars join, or when a neutron star falls apart into a black hole. As the star falls apart, its magnetic fields and rotating energy are turned into powerful beams of high-energy radiation that move through space almost as fast as light. The effects of a GRB would be catastrophic if it occurred within our galaxy, and was directed at Earth. The radiation could strip away the ozone layer, leaving the planet vulnerable to harmful ultraviolet radiation from the sun. It could also trigger a mass extinction event, similar to those believed to have occurred in Earth's past. Fortunately, most GRBs are billions of light years away, sparing our planet from their destructive reach. When a neutron star collapses, it creates gravitational waves, which are ripples in space-time that happen when heavy things speed up very quickly. When neutron stars crash into each other and then fall, they send out gravity waves that are strong enough for LIGO and Virgo to pick up. The information gathered from these discoveries is very helpful in understanding neutron stars, their structure, and how they fall apart. As neutron stars fall apart, they may also send huge amounts of matter into space, which can create bright kilonova. Radioactive decay powers these blasts, which send heavy elements like gold, platinum, and uranium into space. The area around these events gets better because of the junk they leave behind. This helps new stars, planets, and even life form. It's possible that the atoms in your jewelry or the uranium that powers nuclear plants came from a neutron star that was falling. The physics governing neutron star collapse is deeply tied to the enigmatic state of matter at extreme densities. Inside a neutron star, matter exists in a form unlike anything we experience on Earth. Some theories suggest that the cores of these stars might contain strange matter, a hypothetical state of matter that could provide clues about the fundamental building blocks of the universe. Studying neutron star collapses could one day confirm or refute these theories, advancing our understanding of particle physics. Neutron star crashes are very scary because they can happen at any time. Astronomers can find possible possibilities, like twin neutron star systems that are getting close to the end of their lives, but it is very hard to say for sure when or where these events will happen. These disasters could happen at any time in the world, changing the shape of its surroundings in an instant. Heat death of the universe, the eternal silence. Whilst the world is very active right now, it may end up with a fate that is neither powerful nor dramatic, but very quiet. The idea of heat death, which is also called the Big Freeze, imagines a time when the universe stops moving and stays in a state of thermal balance. This situation imagines a universe that is so stretched out and devoid of energy gradients that it turns into a place where there is no sound at all, a haunting, endless quiet. In the early phases of cosmic evolution, energy abounded. Stars burned brightly, galaxies collided, and black holes devoured matter with relentless ferocity. But as entropy increased, a measure of disorder and energy dispersion, the universe steadily marched toward a state where all processes slowed. Over eons, energy became increasingly homogenized, leaving no usable gradients to power even the simplest of processes. It is a cruel paradox of abundance. The universe is full of energy, yet none of it can be harnessed to do work. Stars, the lifeblood of galaxies, play a critical role in this timeline. As the universe ages, the supply of hydrogen, the primary fuel of stellar processes, dwindles. Stars burn through their reserves one by one, leaving behind remnants like white dwarfs, neutron stars, and black holes. These remnants, though fascinating in their own right, emit negligible energy. Over time, even these remnants cool, becoming dark and inert, cosmic tombstones marking the death of a vibrant past. In the heat death situation, black holes also have a strange end. They live on eating matter and energy. They slowly lose mass over unthinkable amounts of time through a process called Hawking radiation. As they get smaller, their release gets stronger, building up to a final burst before they disappear completely. Even though this evaporation is energetic, it only lasts a short time and doesn't do much to stop the eventual fall into silence. The fact that dark energy plays a part in the growth of the universe makes things even more complicated. As this unknown force pulls galaxies farther apart, it becomes less common for celestial things to communicate with each other. Galaxies that used to be busy hubs of activity are now drifting off to their own little areas in space. At some point, particles might stop interacting with each other, leaving a space where motion used to be. The timescales associated with heat death are almost incomprehensible. We speak of trillions of years as mere stepping stones in the timeline of universal decline. Long after the last star has faded, even atomic particles may decay, leaving behind only faint whispers of their existence in the form of low-energy photons and neutrinos. This final state, where the universe reaches maximum entropy, is known as the thermal equilibrium. It is a state where no temperature differences exist, and thus no energy flow or processes can occur. Our knowledge of the universe has been greatly improved by the idea of heat death, even though it is very sad. It fits with the second law of thermodynamics, which says that over time, entropy tends to rise in a closed system. The universe, which is the most closed system there is, follows this rule on a very large scale. It's a sobering lesson of how the laws of physics work on levels that are beyond our understanding. Big Crunch, the universe's catastrophic implosion. The Big Crunch scenario imagines the universe collapsing in on itself, which is very different from the heat death scenario's image of a slow fade into cold nothingness. In the beginning, there was the Big Bang, a violent eruption that set the universe into motion. Galaxies raced outward, carried by the fabric of expanding space-time. For billions of years, this expansion continued, giving rise to the intricate structures we observe today. But the Big Crunch proposes a future where this outward motion halts and reverses, a cosmic retreat into a singularity. The cause of such a reversal lies in gravity, the force that binds the universe together. If the total mass of the universe exceeds a critical threshold, gravity could overpower the expansion driven by dark energy. Over time, this overwhelming gravitational pull would slow the outward movement of galaxies, eventually stopping it altogether. Once halted, the universe would begin to contract. The space between galaxies gets closer as the universe gets smaller. More and more often, stars and galaxies would crash into each other, sending out powerful bursts of radiation and energy. As celestial bodies are torn apart or eaten by giant black holes, terrible things would happen all over the sky. The universe, which used to be very big and open, would turn into a crowded, confusing war zone. On a smaller scale, planets, stars, and even atoms themselves would be compressed under the immense forces of contraction. Temperatures and densities would soar to unimaginable levels, reigniting dormant stars and creating new ones in a final, desperate burst of stellar activity. But this fiery resurgence would be fleeting, as the universe's collapse accelerates toward its ultimate conclusion. The singularity is the center of the Big Crunch. It is a place where all matter and energy come together and have the same mass and gravity. We no longer understand the rules of physics as the world falls apart into this singularity. Space-time would end, putting the universe back to a state that looks a lot like it did before the Big Bang. This singularity could mean the end of the world, or it could mean a possible start over. There are ideas that the Big Crunch might cause another Big Bang, which would make the universe work like a cycle. From this point of view, the universe goes through endless rounds of growing and shrinking, a never-ending cycle of making things and destroying them. Every cycle would wipe out the remains of the last one, making room for a new cosmic era. Although the Big Crunch is still a fascinating theory, current data point to its improbable nature. Scientific agreement has moved away from this model with the discovery of dark energy, an enigmatic component fueling the fast expansion of the universe. The Big Crunch cannot be totally discounted, though, especially if the character or form of dark energy alters with time. This terrible picture of the end of the universe shows how many forces work together to shape cosmic development. It is a sharp reminder of how fragile life is, where even the most basic things like space, time, and matter can become empty at any time. Big Rip, tearing the universe apart at its seams. There is a cosmic disaster scenario called the Big Rip that imagines the end of the world. The Big Rip theory says that dark energy, the unknown force that is speeding up the expansion of the universe, could one day become strong enough to tear galaxies, stars, planets, and even atoms apart. This is different from the Big Crunch theory, which says that gravity is pulling everything together. The idea of dark energy, a still poorly understood factor accounting for around 68% of the universe, lays the groundwork for the Big Rip. Observations of far-off galaxies have shown that dark energy is thought to be the driver of the accelerating universe expansion. Still, one of the biggest riddles of current cosmology is the existence of dark energy, its characteristics, and long-term behavior. In the Big Rip scenario, the strength of dark energy increases over time, overpowering all other forces in the universe. Gravity, electromagnetism, and even the strong and weak nuclear forces would eventually succumb to its relentless pull. As dark energy intensifies, it stretches the fabric of space-time itself, tearing apart the structures that hold the universe together. Billions of years before the Big Rip reaches its ultimate conclusion, its effects would already be felt. Galaxies, bound together by gravity, would begin to unravel. Stars would drift apart from their galactic homes, flung into the void as space itself expands at an ever-accelerating pace. Over time, even smaller structures, planetary systems, and individual stars would fall victim to the growing power of dark energy. The devastation gets ever faster and more terrible as the Big Rip draws near. The relentless expansion of space would rip planets from their orbits into pieces. Stars unable to stay together would break down into clouds of gas and dust. The great forces at work would make the night sky unidentifiable, a disorganized spectacle of ruin and degradation. In the final moments leading up to the Big Rip, the disintegration reaches the subatomic level. Atoms themselves would be torn apart, their nuclei and electrons separated by the overwhelming force of dark energy. The fundamental building blocks of matter, protons, neutrons, and electrons, would cease to exist as cohesive entities. All that remains is an unfathomable, featureless expanse. The possible chronology of the Big Rip is among its most fascinating features. Should dark energy operate in a way compatible with existing data, the expansion of the cosmos may go on endlessly without approaching a catastrophic conclusion. But if the characteristics of dark energy change with time, becoming stronger or operating in ways we cannot now forecast, the Big Rip might happen billions or perhaps trillions of years from now. The precise time frame depends on elements like dark energy's equation of state and its interactions with the fabric of spacetime. While the Big Rip is a theoretical scenario, its implications are profound. It challenges our understanding of the universe's ultimate fate and forces us to confront the possibility that even the most fundamental aspects of reality, space, time, and matter, may be temporary. Unlike other end-of-universe scenarios, which often involve collapse or gradual decay, the Big Rip represents a violent, all-encompassing dissolution of existence. Rogue white holes, explosive portals of chaos. Theoretically, white holes are the opposites of black holes. They are cosmic events that live on the edge of what is possible and what is not possible. Unlike black holes, which eat everything in their path, white holes are thought to violently push matter and energy away, leaving behind a completely destroyed world. Even though white holes haven't been seen with the naked eye, the ideas behind them are both interesting and scary. A white hole is thought to be the reverse of a black hole in every way. While a black hole traps anything that crosses its event horizon, a white hole would eject matter and energy continuously, making it impossible for anything to enter. In essence, it would behave like a cosmic fountain, spewing out material with incredible energy and intensity. The origins of such an object, however, remain speculative. Some theories suggest that white holes could form as the other end of a black hole, potentially connected via a wormhole. If there are rogue white holes, their very existence could be very bad. A rogue white hole might just float through space without any plans. This is different from black holes, which tend to stay close to the centers of galaxies. As it moves, it will send out huge amounts of high-energy particles, radiation and matter, leaving behind areas of chaos and damage. If a star, planet, or other heavenly body got too close to a white hole, it would be slammed with this constant radiation and probably be broken down into atoms in a matter of seconds. The energy emitted by a rogue white hole would dwarf even the most powerful supernovae. The ejected matter, traveling at nearly the speed of light, could impact surrounding objects with unimaginable force. This would generate shockwaves capable of devastating entire star systems. The radiation released would sterilize vast regions of space, rendering them uninhabitable for any form of life. White holes are interesting from a scientific point of view because they make us think about time and chaos. Irreversibility is a very important idea in black hole physics. Once something crosses the event horizon, it is gone for good. In contrast, white holes would go against this rule, pushing out matter that might have been caught inside a black hole, which would seem to reverse the flow of time and entropy. If these things exist, they might hold the key to unlocking the secrets of how the world began and what will happen to it in the end. The potential detection of a white hole would be a monumental event in astrophysics. Unlike black holes, which are identified by their gravitational effects on nearby objects, a white hole would likely be detected through its intense radiation and energetic particle outflows. However, the very nature of these emissions could make observation challenging. The sheer power and chaos surrounding a white hole would obscure its core, making it difficult to study. White hole theories also stretch to cosmology and universe origin. Some scientists hypothesize that the Big Bang itself may have been a massive white hole event, ejecting all the matter and energy that presently shapes the universe. This theory links white holes to the most basic concerns about existence, connecting them to the beginning of time, space, and everything inside. White holes are still a hypothetical concept, a fascinating prospect in theoretical physics. However, their possible existence, particularly as renegade occurrences, serves as a disturbing reminder of how much we still don't comprehend about the cosmos. In a universe teeming with black holes, supernova, and quasars, the idea of an explosive, matter-spewing abnormality roaming the emptiness adds a new level of uncertainty. If a rogue white hole were to pass through a galaxy, it could leave behind a trail of destruction unparalleled by any other cosmic event. Stars would be shredded, planetary systems annihilated, and the delicate balance of galactic structures disrupted beyond repair. The very fabric of space-time might be warped in its vicinity, creating an environment where the laws of physics break down. While no evidence of white holes currently exists, the mere theoretical possibility is enough to ignite both fear and curiosity. In a universe as vast and mysterious as ours, even the most speculative concepts demand consideration. Dead zones of the universe, lifeless cosmic wastelands. There are places in space called dead zones, where the amount of matter is so low that the normal processes that make stars and galaxies can't happen. In contrast to cosmic gaps, which are huge areas with no matter at all, dead zones usually have only a small amount of gas and dust. Conditions in these areas, on the other hand, are so bad for star formation that they look like they've been stuck in time and are always empty. The depletion of star-forming material is one likely reason for these zones. Many times, galaxies in these areas might have previously experienced a burst of star creation that ran out of gas and dust. The galaxies drift into darkness, their surviving stars burning out one by one without fresh material to maintain this process. These regions grow empty over time, inhabited just by the traces of long-dead stars and weak, diffuse gas clouds. Furthermore, influencing the formation of dead zones is the impact of large-scale cosmic occurrences. Star-forming material from galaxies can be expelled by supernovae, galactic collisions, and the energy outflows from active galactic nuclei, hence driving it into intergalactic space. This technique leaves behind a barren wasteland by cutting off these areas of the raw components required for life and activity. Dark matter may also play a role. In areas where dark matter density is insufficient to exert the gravitational pull needed to gather gas and dust, the building blocks of stars cannot coalesce. These regions remain gravitationally quiet, unable to foster the dynamic interactions that lead to the formation of stars and galaxies. The result is a cosmic stagnation that contrasts sharply with the energetic environments of galactic clusters and star-forming nebulae. Dead zones are not just limited to the space between galaxies. Even within galaxies, there can be pockets where star formation is suppressed. These areas, often found in the outskirts of large galaxies, are influenced by gravitational forces, radiation, and the movement of interstellar gas. Known as galactic deserts, these regions may appear as dim, featureless patches when viewed through telescopes, offering little evidence of activity or evolution. Studying dead zones is very important for understanding how galaxies die and how the world moves. Astronomers can learn more about what stops star formation and what keeps galaxy ecosystems going by studying these areas. Also, dead zones are great places to study how stars change over time because they let us see the universe in its quieter, less well-known times. Even though they are empty, dead zones have an eerie beauty. They tell us that the world is not a single bright spot, but a complicated mix of life and death, growth and decay. Even though the silence in these places is scary, it shows how fragile the processes are that make stars, planets, and life itself. The erasure field, vanishing realms of existence. Unlike black holes, which trap matter and energy, an erasure field operates on an entirely different principle. It removes all traces of matter, energy, and even information, leaving no evidence that anything was ever there. This phenomenon defies the known laws of physics, representing a catastrophic breakdown of reality as we understand it. The origins of the erasure field theory lie in the interplay of quantum mechanics and cosmological principles. At the quantum level, particles constantly pop in and out of existence in a process known as quantum fluctuation. While this activity is usually harmless and balanced, some theorists speculate that under extreme conditions, such as those found near the boundaries of the observable universe, these fluctuations could amplify uncontrollably. The result? A cascading effect that destabilizes the very fabric of space-time. The way an erasure field destroys things would be different from how a vacuum collapse or a black hole do it. It wouldn't squeeze matter or change the physical state. Instead, it would erase the quantum information that tells us particles exist. This loss of information is deeper than any known physical process because it goes against the basic idea of information conservation, which is one of the most important ideas in modern physics. It is thought that high-energy events, like the clash of advanced particles with unthinkable energies, or the interaction of dark energy with strange states of matter, could cause an erasure field to form. If these things happen, they might make a field in one place, where space-time itself becomes unstable. Whether it's matter, energy, or even light, anything that goes into this field would vanish, leaving behind a space that is not empty but non-existent. An erasure field has very broad effects. Suppose a galaxy wanders into such a field. There would be no obvious evidence of damage, unlike the great violence of a collision or the gravitational pull of a black hole. The galaxy would just vanish, leaving no gravitational waves, radiation, or trash behind. From an outside perspective, the galaxy would seem to have been removed from the ledger of the universe, with no indication of its past existence. The erasure field's prospective expansion is among the most unsettling features. Should the circumstances forming the field continue constant, it may expand, swallowing even more vast areas of land. Theoretically, this runaway effect may cause stars, planets, and whole galaxies to gradually vanish, hence fragmenting the cosmos into a progressively barren void. Although the erasure field is still only a theoretical construct, its research crosses multiple actual scientific fields. Investigating the boundaries of where and how such a phenomenon may develop, researchers looking at quantum field theory and the nature of space-time stability are, furthermore, the idea tests our knowledge of cosmology and begs issues regarding the fate of the cosmos at last. Magnetars, cosmic titans with devastating magnetic fury. These ultra-dense neutron stars possess magnetic fields trillions of times stronger than Earth's, making them the most magnetic objects ever discovered. While neutron stars are already known for their extreme densities and compact sizes, magnetars take this to an entirely new level, wielding magnetic power capable of wreaking havoc on anything within their reach. Magnetars are formed under highly specific and rare conditions. When a massive star reaches the end of its life and explodes in a supernova, its core can collapse into a neutron star. However, for reasons not fully understood, some of these stars develop magnetic fields of unprecedented strength during their formation. These magnetic fields are so intense that they distort the structure of the neutron star itself, creating a highly volatile and unstable environment. Magnetars are distinguished in part by their inclination for starquakes. The surface periodically breaks when the great magnetic forces inside the magnetar twist and stretch its crust, release great volumes of energy. These starquakes generate bursts of X-rays and gamma rays so strong they might momentarily eclipse whole galaxies. Any planet unlucky enough to be in the path of a single such burst from a magnetar would be dead, as the radiation could wipe off atmospheres and sterilize surfaces. The most infamous example of a magnetar outburst occurred in 2004, when a burst from the magnetar SGR 1806-20 released more energy in a fraction of a second than the Sun emits in 100,000 years. Even from a distance of 50,000 light-years, this event temporarily disrupted Earth's ionosphere, affecting radio communications. Had this magnetar been closer, the results would have been catastrophic for life on Earth. Magnetars also exhibit unique behaviors that set them apart from other neutron stars. Their magnetic fields are so strong that they distort atoms into elongated shapes, creating conditions where ordinary chemistry and physics no longer apply. Within a magnetar's immediate vicinity, these magnetic forces can shred matter at the atomic level, dismantling molecules and leaving nothing intact. A magnetar's magnetic field has a huge effect on a huge area, often stretching thousands of kilometers into space. Anything that got too close, like a spaceship, a planet, or even another star, would be hit by forces so strong that they would change the atomic makeup of that thing in a way that can't be undone. People would die, even if they were very close to a magnetar, because the magnetic fields could mess up the electrical activity in their bodies, like in the brain and heart. Though they have terrible strength, magnetars are not fixed permanently in the cosmos. Usually spanning 10,000 years, their great magnetic fields progressively fade over time. They lose their destructive power and change into more stable neutron stars throughout this era. In cosmic terms, though, 10,000 years is a blink of an eye, long enough for a magnetar to wreak havoc on any neighboring star system. Magnetars are also critical to our understanding of fundamental physics. Their magnetic fields provide natural laboratories for studying phenomena that cannot be recreated on Earth. By observing magnetars, scientists hope to uncover insights into quantum mechanics, nuclear physics, and the behavior of matter under extreme conditions. The fact that magnetars exist makes us worry about how safe the universe is. Magnetars are pretty uncommon, only a few dozen are known to exist, but they could be very dangerous if they were to be close to a galaxy with people. Their pollution could be very bad for life and technology, even if they are many light years away. Hawking radiation collapse, the black hole's final breath. Hawking radiation arises from the peculiar interplay of quantum mechanics and the intense gravitational field near a black hole's event horizon. In the quantum vacuum of space, particle-antiparticle pairs are constantly being created and annihilated. Near a black hole, this delicate balance is disrupted. One particle of the pair falls into the black hole, while the other escapes into space as radiation. Over immense spans of time, this gradual leakage of energy causes the black hole to lose mass. This evaporation process is unbelievably slow for a black hole with the mass of a star. It will take a lot longer than the age of the universe for it to become important. But as the black hole gets smaller, the rate of radiation speeds up a lot. In its last moments, the black hole sends out an amazing amount of energy, which can destroy anything nearby with a wave of high-energy particles and radiation. The final seconds of a black hole's life are believed to be extraordinarily violent. The energy released during this collapse is equivalent to the explosion of millions of nuclear weapons, concentrated in a minuscule region of space. This sudden release could have catastrophic consequences for any nearby celestial bodies, vaporizing planets, stars, or any other matter within its radius of destruction. Hawking radiation collapse is particularly alarming in the context of primordial black holes. These ancient remnants, formed during the early universe, are much smaller than their stellar or supermassive counterparts. Unlike the slow evaporation of larger black holes, primordial black holes could already be nearing the end of their lifespans. Their explosive demise might go unnoticed until the very moment of collapse, unleashing bursts of gamma rays and other high-energy phenomena that could pose serious risks to nearby regions of the galaxy. The detection of these final bursts of Hawking radiation is not just a matter of theoretical interest. Scientists believe that studying such events could unlock critical insights into the nature of black holes, quantum mechanics, and the fundamental structure of space-time. Instruments designed to detect gamma-ray bursts and high-energy particles are constantly scanning the cosmos, hoping to catch the fleeting signatures of a black hole's last moments. But this phenomenon also brings up some scary questions. If there are many primordial black holes spread out in the universe, their random collapses could be secret dangers in the universe. The fall of a black hole doesn't leave any signs, unlike other astronomical threats like supernovae or gamma-ray bursts. A primordial black hole that is getting close to the end of its life could suddenly send out deadly radiation with no warning. This makes it one of the most sneaky threats in the universe. There is also a paradox in Hawking radiation. As the black hole gets smaller, its event horizon gets smaller, and quantum physics effects get stronger. This makes me wonder deeply about what a black hole is like at the end. Does it go away completely, leaving a hole? Or does it leave behind some kind of remnant, a very dense core whose makeup we don't know and which goes against everything we know about physics? The answers to these questions are still hard to find because they lie at the point where general relativity and quantum theory meet. The Hawking radiation collapse is a tantalizing potential for societies that can use the energy of black holes as a power source. The amount of energy that is released as a black hole dies is beyond our understanding. In theory, more advanced tools could change or even speed up this process to get energy that can be used. But such efforts would be fraught with unimaginable dangers, as even the smallest mistake could lead to total destruction. Asteroid collisions. Cosmic bullets with planetary consequences. Asteroid collisions are massive space rocks, remnants from the formation of the solar system, travel at extraordinary speeds, packing enough kinetic energy to cause catastrophic damage on impact. While smaller asteroids frequently burn up in Earth's atmosphere, larger ones have the potential to reshape entire ecosystems, or end them entirely. Asteroids vary greatly in size and composition. Some are rocky, others metallic, and a few are rich in carbon compounds. The larger ones, such as those over 1 kilometer in diameter, pose the greatest threat. At this scale, an asteroid could release energy equivalent to millions of nuclear weapons upon impact, creating shock waves, thermal radiation, and long-lasting environmental effects. About 66 million years ago, at the end of the Cretaceous period, one of the most famous asteroid impacts in Earth's history took place. The Chicxulub hole was made when an asteroid 10 kilometers wide hit the Yucatan Peninsula in what is now Mexico. The impact sent 10 billion Hiroshima bombs worth of energy into the air, destroying everything in its path and sending huge amounts of debris into space. This junk blocked the sun for months, creating an impact winter that killed off 75% of Earth's species, including the dinosaurs. Modern science has identified numerous near-Earth objects, NEOs, asteroids and comets with orbits that bring them close to our planet. Organizations like NASA and ESA have developed sophisticated tracking systems to monitor these celestial bodies. Despite these efforts, not all potentially hazardous asteroids are catalogued, leaving the possibility of an undetected impact. The consequences of an asteroid collision depend on its size, speed, and impact location. A strike in the ocean, for instance, would generate devastating tsunamis capable of inundating coastal cities. An impact on land would produce a massive crater, ejecting debris into the atmosphere and causing widespread destruction. If the asteroid were large enough, the resulting dust and ash could block sunlight, triggering a nuclear winter scenario and collapsing global agriculture. Asteroid collisions are not confined to Earth. The Moon, with its countless craters, bears witness to a violent history of impacts. Similarly, Mars and the gas giants have been struck by asteroids and comets, sometimes with dramatic results. In 1994, the fragments of comet Shoemaker-Levy 9 collided with Jupiter, creating enormous scars in the planet's atmosphere and demonstrating the immense power of such collisions. And scientists are looking into a number of different ways to reduce the risk of asteroid strikes. Changing an asteroid's path is one way to steer it away from something. Kinetic impactors, which are spaceships that hit the asteroid and move it to a safer path, could be used to do this. The gravitational tractor is another idea. This is where a spaceship would use its own gravity to slowly change the path of an asteroid over time. Even though these methods look good, they need to be found early on in order to work. In the past few years, people have also become interested in the idea of mining comets. There are important metals on some asteroids, such as platinum, gold, and rare earth elements. Companies and space agencies are looking into whether or not it is possible to get these materials. Asteroid mining offers exciting chances, but it also brings up moral and practical concerns about the possible dangers of sending an asteroid hurtling toward Earth by accident. Another thing to think about is how the threat of an asteroid crash might affect people's mental health. Realizing all of a sudden that an effect is going to happen could cause broad fear and social problems. In order to handle the disaster, preventative steps must be coordinated and resources must be mobilized. This can only be done through good communication and global unity. Solar flares, the sun's unpredictable wrath. When magnetic energy stored in the sun's atmosphere is released, these rapid, powerful bursts of electromagnetic radiation and energetic particles happen. Solar flares can make beautiful auroras on Earth, but they can also mess up modern technology, hurt satellites, and put humans in danger in space. Solar flares are graded based on their intensity, using a classification system that ranges from C-class, minor, to M-class, moderate, and X-class, extreme. Each category represents a tenfold increase in energy, with X-class flares being the most intense. Within these categories, the strength of a flare is further refined by numerical values, such as X1, X10 or higher. The largest flares can release energy equivalent to billions of nuclear bombs, radiating across the entire electromagnetic spectrum. One of the most infamous solar flares in recorded history is the Carrington event of 1859. This X-class flare caused massive geomagnetic storms on Earth, leading to widespread disruption of telegraph systems, the primary communication technology of the time. Auroras, typically confined to polar regions, were seen as far south as the Caribbean. Had a flare of similar magnitude occurred today, the impact on our technology-dependent society would be catastrophic. Solar flares often occur in conjunction with coronal mass ejections, CMEs, where the Sun hurls billions of tons of charged particles into space. When these charged particles collide with Earth's magnetic field, they can induce geomagnetic storms. These storms pose a severe threat to power grids, satellite systems, and communication networks. In 1989, a geomagnetic storm triggered by a solar event caused a blackout across Quebec, Canada, leaving millions without power for hours. The effects of solar flares extend beyond Earth. Astronauts aboard the International Space Station, ISS, and future missions to the Moon or Mars are particularly vulnerable to the high-energy radiation from these events. Without adequate shielding, exposure to solar radiation can increase the risk of cancer and other health issues. Space agencies closely monitor solar activity and provide warnings to ensure the safety of astronauts during periods of heightened solar activity. Satellites in orbit are also at risk from solar flares. High-energy particles can interfere with satellite electronics, causing malfunctions or complete system failures. GPS signals, vital for navigation and communication, can be disrupted by increased ionization in Earth's upper atmosphere. These disruptions can have cascading effects on aviation, shipping, and military operations, highlighting the interconnectedness of modern infrastructure. Solar flares have great scientific value, even if they have destructive power. Understanding the Sun's magnetic field and its complicated activity helps scientists by means of analysis of these phenomena. Improved forecasting skills are made possible by the way observatories like NASA's Solar Dynamics Observatory, SDO, and the Parker Solar Probe have transformed our capacity to view and examine solar activity. Forecasting solar flares is a difficult endeavor. While scientists can detect areas of the Sun with increased magnetic activity, determining the precise timing and amplitude of a flare is challenging. Advances in computational modeling and real-time observation have improved predictions, but the Sun's behavior is still unpredictable. The development of space weather forecasting systems, such as NOAA's Space Weather Prediction Center, is critical in reducing the effects of solar events on Earth. Preparing for solar flares involves a combination of technological and policy measures. Power grids can be equipped with protective systems to handle sudden surges in voltage caused by geomagnetic storms. Satellites can be designed with radiation-hardened electronics to minimize damage from high-energy particles. International collaboration is essential to coordinate responses to solar events, ensuring that global infrastructure remains resilient in the face of potential disruptions. Blitzar collapse. The sudden death of a neutron star. Consider a neutron star, the collapsed core of a huge star so tightly packed that a teaspoon of its substance weighs as much as a mountain. If specific conditions are satisfied, this massive revolving star can collapse into a black hole, releasing a huge explosion of energy and wreaking havoc in its path. Neutron stars, remnants of supernova explosions, are among the most extreme objects in the universe. They can spin rapidly, some at rates exceeding hundreds of rotations per second, and generate immense magnetic fields. However, not all neutron stars are destined to remain stable. A Blitzar occurs when the balance holding a neutron star intact is disrupted. Specifically, the centrifugal force from rapid rotation can temporarily counteract the intense gravitational pull, trying to crush the star further. But over time, rotational energy is radiated away, weakening the star's ability to resist its own gravity. When this delicate equilibrium fails, the neutron star collapses into a black hole. The collapse releases a massive burst of electromagnetic radiation, including gamma rays, radio waves, and X-rays. This phenomenon is often detected as a fast radio burst, FRB. A sudden powerful flash of radio energy lasting only milliseconds. These fleeting bursts have puzzled astronomers for years, but blitzars are one of the leading theories behind their origin. The mechanics of a blitzar collapse are as fascinating as they are terrifying. As the star's core succumbs to gravity, its magnetic field, already one of the strongest forces in the universe, intensifies briefly before being swallowed by the forming black hole. The energy released during this process can outshine entire galaxies for a brief moment. Observers from a safe distance would witness an extraordinary but ephemeral flash of light, followed by the silence of a newly formed black hole. The aftermath of a Blitzar collapse is equally remarkable. The surrounding space is altered by the sudden formation of the black hole. Nearby matter, if present, is drawn into its event horizon, where time and space warp irreversibly. This process might also generate additional bursts of energy, creating a cosmic beacon visible across billions of light-years. Blitzar collapses are not just theoretical curiosities, they hold significant implications for understanding the universe. For instance, their study helps scientists probe the mysteries of neutron star physics, including the limits of matter under extreme density and pressure. They also provide insight into black hole formation, offering a glimpse into one of the most enigmatic phenomena in the cosmos. The detection of Blitzars is a relatively new frontier in astronomy. Fast radio bursts, first discovered in 2007, remain one of the most mysterious signals from space. While many FRBs appear to originate from galaxies billions of light-years away, some exhibit patterns or repetitions, leading to debates about their sources. Blitzars, as a potential explanation, emphasize the role of neutron stars in these extraordinary emissions. Interestingly, the conditions required for a Blitzar collapse are incredibly rare. Neutron stars with just the right mass, rotation rate, and magnetic field strength are needed to set the stage for this dramatic event. This rarity makes each observed or hypothesized Blitzar a unique cosmic laboratory. Blitzar's possible threats, albeit remote from Earth, are nonetheless worth considering. The energy that is released during a crash could destroy any planets or systems that are close by. If the Blitzar gets close enough, it could send high-energy radiation toward Earth, which would damage gadgets and put people at risk. Luckily, because space is so big, these kinds of things aren't likely to happen in our galaxy. Blitzars are also important to the story of the universe as a whole. They show the extremes of how stars change over time as part of their life cycle. Blitzars show how the universe is always changing and becoming more chaotic, from when they were young and huge stars to when they explode in supernova and neutron stars, and finally when they turn into black holes. Astronomers are still very interested in the search for Blitzars. Scientists hope to find more proof of these huge crashes with the help of advanced tools like the CHIME telescope and soon-to-be-built grids that can pick up radio waves. Each new finding not only helps us learn more about Blitzars, but it also makes us appreciate how complicated and changing the world is even more. Phantom energy destruction. The universe's accelerating doom. Phantom energy is a possible type of dark energy. It is one of the darkest ideas about what will happen to the world in the end. Dark energy is one of the biggest mysteries in astrophysics. It is the unknown force that is speeding up the growth of the universe. Phantom energy, on the other hand, takes this idea even further by imagining a worst-case situation that could cause the universe to break apart, galaxy by galaxy and atom by atom. The usual explanation for dark energy is that it acts like a soft, steady force that fights gravity and speeds up the growth of the universe. Phantom energy, on the other hand, suggests a force that is much more hostile and harmful. It takes on the form of energy that has an equation of state constant, WW, that is less than -1. This means that ghost energy would not only make space bigger, it would do so at an ever faster rate, which would have terrible effects. The imagined consequences of phantom energy start out somewhat benignly. Galaxies would first float further apart, as in the conventional paradigm of cosmic expansion. But when phantom energy's impact rises, its repercussions would become more intense. Galaxies themselves might be wrenched apart, stars and planets detached from their gravitational bonds. Even solar systems would not remain whole eventually. The next phase of destruction would target individual stars and planets. The tidal forces caused by phantom energy would overwhelm the gravitational forces holding these celestial bodies together. Planets would crumble, and stars would be pulled apart in a cascade of cosmic chaos. The universe, once a tapestry of structured matter, would devolve into a fragmented wasteland of particles. But phantom energy's destructive potential doesn't stop at celestial objects. As its influence grows, it would eventually reach down to the very fabric of matter itself. Atoms, the fundamental building blocks of the universe, would be stretched beyond their limits. Electrons would be torn from nuclei, and even the strong nuclear force binding protons and neutrons together would fail. In this ultimate cataclysm, the universe would dissolve into a sea of unbound particles, racing outward in a final chaotic expansion. The concept of phantom energy also has profound implications for the nature of the universe. If it exists, it would challenge many of our fundamental assumptions about physics, including the conservation of energy and the stability of the vacuum. The idea that the universe could self-destruct under the influence of a force intrinsic to its very structure is as fascinating as it is terrifying. Although the study of phantom energy is hypothetical, actual scientific investigation drives it. Strong evidence for the presence of dark energy has come from observations of far-off supernovae and cosmic microwave background radiation. Its precise form is still unknown. Some theoretical models suggest that dark energy may change with time to become phantom energy. By use of observational data, these models are evaluated to improve our knowledge of the expansion of the universe. Phantom energy also invites intriguing philosophical questions about the nature of existence. If the universe is destined for a big rip, what does that mean for the legacy of galaxies, stars, and civilizations? Could advanced civilizations find a way to escape or counteract phantom energy's effects? Or would they too be swept away in the final cosmic tide? When we study phantom energy, it pushes the limits of what we think we know about the universe. Researchers learn more about the limits of physics and how the world works in strange situations by looking into these kinds of unusual situations. Observations and experiments, like those done with the Hubble Space Telescope and the soon-to-be-built James Webb Space Telescope, may help show if phantom energy is a real threat or just a theory. The infinite fracture, the terrifying multiversal splintering. Imagine a world where space, time, and causality, the very things that make reality possible, fall apart in an instant. As a result of quantum instability, our world could break apart into an endless number of different realities. This terrible event is called the infinite fracture. The idea of multiple universes is often interesting to scientists and philosophers, but the infinite fracture turns this idea into a nightmare on a cosmic scale. The concept stems from the idea of quantum superposition, where particles can exist in multiple states simultaneously. This fundamental principle of quantum mechanics suggests that our reality is just one of many possible outcomes. In normal circumstances, quantum interactions stabilize into a cohesive reality that we perceive as the universe. However, in the case of the infinite fracture, this delicate balance is obliterated. A catastrophic event, whether it be a collision of higher dimensional branes, the destabilization of quantum fields, or a vacuum collapse, could cause this fragile equilibrium to shatter. The infinite fracture would result in every quantum possibility occurring simultaneously, tearing apart the coherence of reality. Every moment, decision, and possibility would unfold at once, creating an incomprehensible kaleidoscope of alternate realities. For sentient beings, this would be a fate worse than annihilation. Consciousness, tied to the fabric of space-time, would be unable to adapt to the chaos. A single thought could splinter into countless contradictory streams, leaving minds trapped in an eternal state of disarray. There would be a huge mess of worlds colliding as stars, planets, and galaxies broke apart into an endless number of different shapes. Already under a lot of stress, the universe's gravity fabric would break under the weight of all the different versions of itself. Whole galaxies could blink in and out of existence, with their matter and energy moving around in an infinite number of time periods. The past, present, and future would all merge into one confusing state, and time itself would lose its meaning. Theoretical physicists have hypothesized that such an event would happen should the quantum forces supporting our planet destabilize. A trigger may be a rapid change in the fundamental constants of nature or the interaction of our world with a higher dimensional entity. The prospect that the infinite fracture may start at one spot and spread outward like a chain reaction is even more terrifying. In this instance, it would spread at the speed of light, without opportunity for warning or escape. Surviving the infinite fracture is an impossible concept. Advanced civilizations, no matter how technologically superior, would be unable to shield themselves from the unraveling of space-time. Their greatest achievements would crumble as the fundamental laws of physics dissolved. Attempts to flee to other dimensions or universes would be futile, as the fracture would propagate across all connected realities. Apart from its scope, the infinite fracture is horrible as it leaves no record of what used to be. The cosmos would therefore turn into an incomprehensible mess of overlapping probability, devoid of any clear structure or chronology. It is the ultimate loss of meaning itself, as much as of life or energy. The Cosmic Guillotine, the sudden end of expansion. Consider a scary situation called the Cosmic Guillotine, in which the universe stops expanding all of a sudden and devastatingly. In the Big Rip or heat death, cosmic events happen over billions or trillions of years. The Cosmic Guillotine, on the other hand, imagines that all growth will end instantly, smashing galaxies, stars, and even atoms together in one terrible moment. This terrible potential stems from dark energy, the unknown factor fueling the universe's accelerating expansion. Dark energy is assumed to be a continuous force, represented by the cosmological constant in Einstein's equations. However, if dark energy is not a constant, but rather a dynamic entity linked to an unknown quantum field, its behavior may alter unexpectedly. In the Cosmic Guillotine scenario, this field might abruptly decay into a lower energy state, breaking the universe's expansion equilibrium. If this kind of decay happened, the effects would be felt right away and by everyone. Dark energy would no longer push things away. Instead, the pull of all matter would take over. Galaxies that were moving apart would suddenly change direction and speed toward each other at unimaginable rates. Space-time would snap back after being stretched for eons of growth, sending out shockwaves of energy that are hard to imagine. Big structures like galaxy clusters would be torn apart in an instant, and the matter inside them would be squished into denser and denser states. On a local scale, the Cosmic Guillotine would obliterate entire star systems. Planets would spiral into their stars, and stars would collapse into black holes. Even black holes, typically impervious to external forces, would be pulled together, merging into a single supermassive entity. The immense gravitational pressures created in this cascade would distort the very laws of physics, possibly creating a singularity that consumes everything. The most terrifying thing about the Cosmic Guillotine is how quickly it works. In other end-of-the-world scenarios, there are signs or slow changes that lead up to the event, but this one would happen without warning. Dark energy is controlled by a quantum field that could break down at any time, anywhere in the world. This would start a chain reaction that moves at the speed of light. No matter how far along a civilization was, it would not have time to get ready or leave. The results for space-time are similarly catastrophic. The collapse of expansion would most likely result in a total breakdown of causality, as time and space are compressed into an infinitesimal point. In this final instant, the universe would cease to exist as a cohesive unit, leaving no trace of its past or people. If the mysteries of the universe fascinate you and you want to dive deeper into the mind-bending phenomena shaping our cosmos, don't forget to like this video and subscribe to our channel. Hit the bell icon so you never miss an exploration into the unknown, and let us know in the comments which cosmic terror you'd like us to unravel next. Together, let's journey further into the vast, awe-inspiring void of space.